So our next speaker, we have Dr. Kevin Cannon. Dr. Cannon is an assistant professor of geology and geologic engineering at the Colorado School of Mines. Today he's going to talk with us about lunar ice and mapping. Dr. Cannon?
Great. Well, thank you so much for the invite. And so today I'm going to talk about what we know about ice at the poles of the moon, what we still don't know, and hopefully how we're going to find that out. Next slide. Okay, so when I talk about lunar ice, I like to divide it into these three different distinctions here that are separated vertically. So when I talk about surface ice, I'm really talking about ice at the optical surface in the upper microns to tens of microns. When I talk about shallow ice, I'm talking about ice within the upper meter. And then below that, I'll talk about deep ice as well as an intriguing possibility. Now, it's important to keep in mind when we look at all of these different techniques that have been used to try and detect and characterize ice or hydrogen, that they are all sensitive to a particular depth beneath the surface. And when we combine that, and these are shown here with these arrows, when we combine that with the different spatial resolution of these different instruments, that can make it very challenging to try and reconcile all of the data that we have, but I'm going to attempt to do that in this talk. Next slide. Okay, so starting out with the surface or superficial ice, what we seem to be seeing from these different data sets like LAMP and N-cubed is evidence for a very thin, patchy surface ice or frost layer that is distributed over the cold traps at both the North Pole and South Pole of the Moon. And Bill Farrell and others have concluded that this is a very transient phenomenon, that this surface ice is actually less than a couple thousand years old. And it's part of this very dynamic surface where ice may be being churned up from depth and then mobilized over the surface and removed and lost into space. Next slide. If we continue on then into the shallow ice, I think some of the best data for this comes from neutron spectroscopy. And so this is detecting the presence of hydrogen in the upper about 70 to 100 centimeters that's inferred to possibly be in the form of water ice. And so there are two instruments here. There's LPNS on Lunar Prospector and LEND on LRO. And if you just look at the data now, the neutron spectroscopy has a very large footprint, very low spatial resolution. And so if you just look at the data over the entire poles, you would end up with a very low amount of water equivalent hydrogen or ice, something like tenths of a weight percent or even less. What people have done, though, is they've used some clever processing techniques, things like Pixon reconstruction, where they say, okay, what if all of that signal is coming from just the areas where water ice might be stable? And if you do that, shown in the figure here in the table on the right, then you do end up with slightly higher numbers, so getting up into kind of single-digit weight percent of water equivalent hydrogen in the upper 70 to 100 centimeters. There's also evidence from the neutron data for a dry or desiccated layer of some tens of centimeters thickness right near the surface. All right, next slide. Now, staying at or near the surface, it's also useful to draw this very distinct contrast between the poles of the moon and the poles of Mercury. So in terms of near surface ice, looking for visible signatures or looking for geomorphology, on Mercury, you can literally see the surface ice deposits in visible imagery. And there's some examples here. You can see these bright surface ice deposits in the yellow outlines. And there are also geomorphological features that are consistent with the presence of ice and other water ice and other volatiles. And now, this is very different on the moon, where we really don't see this same type of evidence. So people have looked at the stretched MAC images over the PSRs. They've looked carefully at those images for frost or geomorphologic features that might be consistent with ice, and they have yet to find any. So this is one example here, an abstract from Brown et al. They say that landforms inside two craters likely to host water ice are indistinguishable from non-ice bearing craters. And they also found no definitive evidence for permafrost landforms or surface frost. So there seems to be this quite stark difference between ice near the surface at Mercury and the poles of the moon. Next slide. Okay, and then the other piece of evidence we have for this surface or this shallow ice comes from the L-cross impactor. So, of course, this was a point measurement from one point in Cabeus crater, and the impact excavated a certain depth beneath the surface. And
You have a
um,
hot mic?
And from Tony Collerpete's paper, the canonical value is about 5.5 weight%. And that's kind of an average over that depth that was excavated by L-Cross. Of course, there were other volatiles as well as ice indicated in the table here. Now, some newer analyses have tried to actually look at how that ice may have been stratified within the subsurface. So this work here by Christian Lutzinger looked at these different potential stratigraphies of ice, and there are some degeneracy between these different models, but the best fit had an increasing amount of ice with depth. And there was some evidence for a strong layer at about 5 to 6 meters down that could indicate pore filling ice or potentially excess ice as well. Next slide. Okay, now in terms of the deep ice, there is some circumstantial evidence that there may be much more ice deeper down than the instruments have been able to sense to. So on the left here, this is work by Lior Rubinenko, who found that small craters are shallower than they should be at the south pole of the moon, but not the north pole. And this was interpreted as evidence for a layer up to 50 meters thick with a mixture of ice and dry regolith. Now, on the right-hand side, there's always been some controversy with the radar measurements as to whether or not the circular polarization ratio is uniquely indicative of ice in polar craters. In the latest work here by Brad Thompson, they reanalyzed these statistics here, and they found that there is this uptick in the number of these CPR anomalous craters at the North Pole, but not the South Pole of the moon. So if both of these are showing evidence for subsurface ice, then I think there's a lot more work to be done to try and reconcile why we have, one piece of evidence showing, potential ice at the South Pole, and then the radar showing evidence for ice at the North Pole. We need to, figure out what's going on here. Next slide. Back one. Okay, and then there's also other evidence as well. So this is some brand new work from Ariel Deutsch, who this work has found that there is a topographic softening effect in areas of where water ice is stable within the subsurface. And what's interesting is that this softening effect does not necessarily correlate with the detections of superficial ice from M cubed. And so the implication here is that this topographic softening may actually be due to deeper ice and not ice that's present right at the surface. Next slide. Okay, so then this here is my attempt to try and put all of this together and put forward a self-consistent view with all these different pieces of evidence, all these different data sets. So I think in terms of the surface ice, there's evidence for a thin, very patchy frost that may be a transient phenomenon. And this doesn't appear to be enough to even be visible in these stretched NAC images. We can only see it with some of the spectral data. Beneath that, in the shallow ice zone, there seems to be evidence for a desiccated zone, some tens of centimeters thick. This is coming from the neutron data. And then beneath that, there's perhaps up to about 1 weight% ice that's likely finely disseminated in the regolith due to billions of years of impact gardening. That's consistent with the neutron data and also with models of regolith gardening, for example, the work by Emily Costello. And then deeper down, I think this is the most intriguing area where we have a lot of circumstantial evidence that there could be thicker layers, maybe more pure layers of subsurface ice, meters or tens of meters beneath the surface. But I think a lot more work needs to be done to interrogate whether that's actually the case and to characterize the deeper layers in the cold traps at the poles. Next slide. Okay, so how are we going to move forward and continue to build our understanding of the lunar volatile cycle and these ice deposits at the poles? So there is a slate of new missions on the books. There are a lot of these CubeSats and SmallSats that are going to look at the poles. And I think these missions in particular are likely to refine our existing observations, mostly for the surface ice. A lot of these are using techniques that are sensitive to just the optical surface. But I'm not sure that these are going to resolve a lot of the questions that we have about the shallow ice and particularly the deep ice, which is of most interest to me. Next slide. Okay, now, of course, what we really want to do is get onto the ground and really get some ground truth for these orbital observations. And one of the best chances to do that upcoming is the Viper mission that's set to launch in late 2023. So Viper has a 1 meter deep drill. It also has a host of other instruments, spectrometers, neutron spectroscopy. And so this is going to be really good for getting us the first kind of ground truth of some of these orbital observations. Next slide. Now, there are a couple of challenges here and some limitations that we should keep in mind. So that 1 meter deep drill, that's great. It's going to have these nice 10 centimeter bites to look at the stratigraphy, but that's not quite going to get down into the deep ice. And so we might want to think about future missions and future techniques that we'd be able to drill deeper down into the subsurface in these cold traps. Next slide. And then I think one of the main challenges is that Viper is going to map a very small area at poles. And the question is going to be, how can we take that, how can we take those results and extrapolate them or map them onto the broader South Pole and also the North Pole as well? So shown to scale here, the total area of permanent cold traps at the poles, this is work by Jean-Pierre Williams, is over 18,000 kilometers squared. And shown to scale here, the Viper anticipated mapping area is going to be about 0.005 kilometers squared. So it's going to be a real challenge here to take those results and then translate them to areas that are away from the mapping area. Next slide. All right, and then I think another way that we can continue to build our knowledge about the ice deposits and the polar regions is modeling studies that are supporting these missions, especially in the interstices between when we have these active missions. And so I'm going to talk about just a couple of modeling efforts that I've been involved in to try and piece together some of this story. So the first is something called the Ice Favorability Index, or the IFI. And what this is a forward predictive model of which areas of the poles are most likely to host rich deposits of ice, particularly in the subsurface. So this takes into account not just the thermal environment and how it's changed over time, but also things like the age of the surface, which is really important for when ice could have started accumulating in a particular cold trap. Now, currently, these mapping products are only about 250 meters per pixel. So there's opportunities to do more local scale work. And then, of course, this data, this model has never been ground truth. So we don't actually know if areas that are identified as hotspots here actually correspond to higher ice concentrations on the ground. And that's something that we could start to do with the Viper mission by comparing the ice favorability index maps with what's mapped on the ground. Next slide. The other modeling work I've been doing is to really try and understand how all of the different geologic processes, so ice deposition, regolith gardening, ice loss processes, how all of those work together to build up these stratigraphies of ice within the subsurface. So this is a model called Ice Stack, and this is a fully three-dimensional stochastic ice deposition and regolith gardening model that I've been working on for some time. Some of the new features here shown on the left, it's now able to take in ice stability depth maps for a certain area, and those can change over time. So it's not just ice stable everywhere. It varies with XY location. And then on the right here, I'm showing just the really strong stochastic effects that you get in these models. So these are cross sections through the models. They're down to about 30 meters deep. And these are 3 different runs with the exact same starting conditions. And the only thing that's changing here is the exact impact history of how ice has been delivered to the polar regions, mostly by hydrated asteroids. And so you can see these remarkably different model results that you end up with. And so this is something, again, that can be ground truth by comparing an ensemble, a larger ensemble of these models with stratigraphies that are identified on the ground. Next slide. Okay. So I think ultimately, to really fully increase to capture the true story of lunar volatiles, this is going to come with the buildup of commercial activity and missions like prospecting and extraction of ice at the poles. Next slide. Now, this is, of course, a little bit controversial, there are some scientists who don't really like this, but I think we do have to contend with the reality here, and we can look at the opportunities that this provides. So if we look at what's actually happening here, there's really no appetite for a widely ratified international treaty to replace the Outer Space Treaty. And instead, what we're seeing are bilateral agreements like the Artemis Accords that explicitly reinforce that space resources can be used and extracted under the existing OST. We're also seeing a growing number of individual countries pass legislation giving their own citizens and corporations ownership rights over resources mined in space, and that includes ice on the moon. So I want to talk about how this can really build our understanding of the polar stratigraphy at the moon's poles. Next slide. Okay, so this is a completely made up chart with made up data, but what I'm showing here on the y-axis is the amount of data or the amount of knowledge we have about ice at the moon. And right now, all of our knowledge is coming from these government spacecraft missions led by space agencies. But very soon in the near future, we're going to see commercial companies start to collect data from prospecting and exploration missions. And given the pace of the private industry, I think we can anticipate in fairly short order there will be this crossover point where the majority of the data from the lunar poles is coming from commercial companies. So we have to think about what that actually means, because in, for example, terrestrial oil and gas or mineral exploration, data is itself a commodity. It is bought and sold, and it's often proprietary, which is very different than what we're used to with, for example, the NASA PDS. Next slide. So we're thinking about how this might work at the Colorado School of Mines, and one potential model, and this is again drawn from the terrestrial world, is something like a lunar ice data sharing consortium. So the way this would work, and these are completely hypothetical companies, but let's say, for example, that Lunar Outpost goes and explores Sverdrup crater at the South Pole. Maybe Blue Origin focuses on Shoemaker crater, and maybe Astrobotic has a prospecting campaign over the North Pole of the Moon. What could happen is that these companies could agree to buy into this data sharing consortium. And then even though they haven't explored the entire poles themselves, they could take advantage of the data sets from other players who have missions to those other regions. Now, if this kind of consortium is hosted by something like a university, a third party, then that provides a mechanism to get some of this data into academia and be used for research and teaching purposes. Next slide. And there's a lot of precedent for this. So not just for the data itself, but also the samples. So if you go into any geology department in the country, you'll see boxes of core samples that have been donated by industry for research and teaching purposes. You'll also see that any grad student working on an oil and gas project or a mineral exploration project, they're almost certainly using data from industry as well. So I think this is something that, if we look at the bright side of this increasing commercial activity, I think this is going to open up access to more data and more samples of polar ice deposits than we ever would just from space agency missions alone. Next slide. Okay, so to wrap up and conclude here, I think we, in the past few decades, we've made tremendous progress in our understanding of the poles following these early predictions by Harold Urey, and then the canonical papers by Watson et al. And Arnold predicting that ice could be cold trapped in polar craters. A synthesis of observations that is, I think, consistent with a lot of these data sets would be something like a patchy transient frost at the surface, and that optical surface, maybe up to about 1 weight% or so ice underneath a desiccated layer. And then potentially larger reservoirs at meters to tens of meters depth. But this is where we have the most uncertainty. We really don't know if this deep ice actually exists, and if it does, what its characteristics are. And I think that's a particular focus for the future. So as I said, there's still a ton that we don't know, particularly about the shallow and deep ice in the subsurface. Some of the new knowledge will come from additional orbital missions, but I think it is time that we really do get down and focus on surface exploration as well. And Viper is going to be a good first step for that. And then, of course, I think it's good to have a robust modeling efforts in the background as well. And I think commercial activity, so prospecting and extraction, I think this will give us more data and samples than we could ever dream of from government missions alone. With that, I will wrap up, and I'd be happy to take any questions or look in the chat if there's not enough time. Thanks.
Fantastic. Thank you very much, Dr. Cannon, for that neat talk about the lunar ice and mapping that ice. I believe we may have time for one question here. Um, it says, in the ice stack model, do you take into account that the impactor can also make water due to the transient temperature changes?
Yeah, so there is impact melting taken into account. So when a crater event happens, there is an area that's calculated around the point of the impact where vaporization of that ice can happen, and then so that ice is assumed to be lost from the environment.
Okay. And unfortunately, that's all the time we have for questions, and we will be moving on to our next speaker.